Hello viewers, you are welcome to Joe Newton online class. In this class, we want to treat an important concept in physics, of course, under electricity, and that is simple AC circuit. Specifically, we want to look at reactance in an AC circuit. Now, by way of introduction there, what we mean by an AC circuit? Of course, that is a circuit of an alternating current. When we talk about alternating current, we mean that current whose value or that current that varies periodically so that its direction reverses periodically. That is an alternating current. Remember, we still have direct current, the current that flows in one direction. Now, in that AC circuit, we have important components. That is the resistance, the capacitance, and the inductance, which are products of resistor, capacitor, and the inductor. These are the components that offers these oppositions I mentioned. Good. Now, we want to look at what happens in an AC circuit, simple AC circuit. What happens in an AC circuit when we have capacitor in that AC circuit that offers capacitance? When we have resistor in that AC circuit that offers resistance? When we have inductor in the AC circuit that offers inductance? Then from that we'll be able to deduce the reactance. Of course, we have the capacitive reactance and the inductive reactance, that is respectively. Now, first of all, in an AC circuit, we have key nomenclatures. These nomenclatures include what we call a current, that is the instantaneous current, is given by I naught sine 2 pi f t. Of course, we know that omega is equal to 2 pi f. So I is equal to I naught sine omega t. This sine omega t here, this I is the instantaneous current at a particular time, while I naught is the peak current, the maximum current value at a particular time. Then the sine omega t here, the omega t is what we call the phase angle with which one of the components may lead or lag, depending on the system. Then f is the what? Frequency. Okay, similarly, we have in the case of V, the voltage. Of course, it is the voltage that produces the current. The voltage, we have V is equal to V naught sine omega t, while V is the instantaneous voltage, V naught is what? The maximum or peak value of the voltage in that AC circuit. Good. With this concept, it leads us to what we call the IRMS, that is the root mean square current, which is the effective value of current in an AC circuit. That root mean square current simply means we denote it by IRMS, root mean square current. That is that steady current which will develop the same quantity of heat in the same time in the same resistance is known as RMS current. That is root mean square current. Of course, it is given by IRMS is equal to I naught over root 2. That is the formula. We shall apply this formula in subsequent classes when we shall be treating calculations proper in AC circuit or RLC circuit, that is resistance, inductance, capacitance circuit. Okay, so this is IRMS, which is the effective current. Now, let's look at what happens in an AC circuit when we have a resistor in it. So when we have a resistor in an AC circuit, what happens to the current and voltage is what we are looking at. In that case, both the current and voltage are said to be in phase. Both of them are in phase. No one is leading and no one is lagging. They are balanced. They are at par in their contribution in the circuit. So in that case, we have that V and I are in phase. Okay, I and V are in phase when we have resistor in an AC circuit. It is noted by the symbol here, like small rectangular box, or R, that's a resistor. Now, this is typical AC circuit. This is the alternating current. Now, let us look at what will happen when we have capacitor in an AC circuit. When we have capacitor in an AC circuit, it will now happen that the current will lead. The current will lead while the voltage will lag. Now, at what phase angle will the current lead? That's the next question. The current leads. In this case, this is capacitor. Capacitor in AC. This is resistance in AC. That resistor in AC. So in this case, this symbol is symbol for capacitance. Make sure you distinguish it from that of cell. In cell, we have that these two lines, one is longer than the other, indicating the positive and negative. But for capacitor, we use the two parallel lines representing the two parallel plates of the capacitor. So when capacitor is connected in a circuit offering capacitance, we have that the current, which is IC, leads VC by 90 degree. That the phase angle is 90 degree, that right angle, or 1/4 cycle. Of course, 90 is equivalent to 1/4 cycle, or pi/2 radian in radians. Yes, pi/2 radians. Good. Then, if you want to represent it vectorially using the vector representation, we shall have that the symbol will be like this by vector representation. This is our IC. This is the VC. So it will go like this. I is leading. Now, when we look at this is what happens here. Then, in the case of inductance, we use the letter L for inductor. In the case of inductance, we have inductor in an AC circuit. Case of inductance, what happens there? When we have inductor in an AC circuit, what happens is that the voltage leads the current. The voltage leads the current. So here, VL, that the voltage of the inductor leads IL. Voltage leads by the same phase angle, by right angle 90 degree, or 1/4 cycle, or pi/2 radians. So this is what happened. So be mindful of these two components and their effect in an AC circuit. So in this case, the voltage leads. When you have capacitance, the current leads. And the phase angle in both cases is right angle, that is 90 degree. When current leads here, the voltage is said to be lagging behind. The voltage lags. When voltage leads here, the current lags. Then vectorially here, using vector representation here, using vector, it should be like this. You have V and I. So using vector here, you have that here is our IL. You have our IL. Then that is our VL. So in this case, the voltage what leads. So V leads. V leads. This is right angle, the phase angle, angular difference, right angle, 90 degree. So here V leads. Now, if we now use this equation, basic equation of identification of AC to represent what happens to the current, in the case of capacitor, this I sine omega t becomes I sine omega t, I sine bracket open omega t plus pi/2. because the phase angle increases. It leads with phase angle of what? 90 degree. This is what the equation will be, the instantaneous current will be in the case of capacitance in an AC circuit. So we have this here, that I is equal to I naught sine bracket open omega t plus pi over 2 for here, because current leads. But in this case, because voltage leads, what we now have here, and the current lags behind, we now have here I is equal to I naught sine bracket open omega t minus pi over 2 because the current here lags behind by, that is, the instantaneous current here lags behind by 90 degree or pi over 2 radian. So that is it. So with this, I believe by this introduction or pre-explanation, you'll be able to distinguish between the effect of capacitance in an AC circuit